Hi, my name is Sylvain Marron and I am going to show you remote controlled Heli Aerodynamics. First of all, I would like to say sorry for my bad English and my bad accent. I hope you will understand me. So, this PowerPoint is for newbies in RC Heli who want to understand Heli aerobatics. In the first part, we will see the flight theory. We will see the blades and what is swash plate, and we will see collective pitch and cyclic pitch, and finally we will see the function of tail rotor and flybar. Let's start with blades. Blades have a symmetrical section. In other words, contrary to the figure shown here, the shape is the same above and below. Symmetrical section allows inverted flight, but some models use asymmetric section because they don't need to do inverted flight. Blades have the same behavior than aircraft wings. Lift is due to speed, so for Heli is blade rotation speed, and angle of incidence or pitch. On RC Heli we use a constant rotor speed, so to modify the lift, we will modify the pitch. What is the pitch? The pitch is the angle between the blade and the horizontal line. We name it also angle of incidence. Low pitch gives low lift, and higher pitch will produce higher lift. The lift is due to a difference of pressure around the blade. There is a low pressure above the blade and a high pressure below the blade. We notice that the low pressure is bigger than the high pressure. So the air does not carry the helicopter but attracts it upward. Now we will see the swash plate. This is a component of the rotor. It transmits orders to the main rotor. Orders will be translated into pitch variations. It is located around the main shaft. The main shaft is here. And the swash plate has two plates, an upper rotary plate and a lower fixed plate. Both plates are linked together by a bearing. Upper plate is linked to blades and it turns with the rotor. The lower plate is linked to servos and receives orders. Now let's see swash plate operating. The main shaft, the swash plate is here, okay? So the main shaft, blades and the upper upper swash plate are linked together and rotate together. Linkage rods tilt or move up or down the lower swash plate, which moves the upper swash plate. Then tie rods move up or down the blade and then modify the pitch of each blade. So, on the swash plate we can apply two sorts of command: the collective pitch and the cyclic pitch. We will start with the collective pitch and next we will see cyclic pitch. So, collective pitch. Collective pitch works on all blades uniformly. Collective pitch is used to move up or down the helicopter. We will see on this figure. When the swash plate moves up, pitch of all blades increases. Then lift increases. When lift is greater than the helicopter weight, then the heli moves up. When the swash plate moves down, all the blades have a lower angle and the pitch decreases. Then the lift decreases too. If the lift is less than the weight of the helicopter, then the helicopter moves down. Now let's look at the collective effect on the whole rotor area. On the left, the heli is hovering. Lift is equal to the weight. And we can see that the lift remains constant on the whole rotor area. On the right, we give an order to move up to the heli. Then the swash plate moves up. Blade pitch increases, so lift increases too, and we can see that the lift increases on the whole rotor area uniformly. Then the helicopter moves up, remaining in horizontal position. Now we will see cyclic pitch. The cyclic pitch gives a different pitch depending on the rotary blade position. For example, when the blade is in the front, it has a different pitch than when it is in the rear position. So, during a total turn, the pitch of the blade changes. This command allows tilting the helicopter forward, backward, or on the side. Let's see on a figure. When swash plate tilts forward, pitch of the front blade decreases. and pitch of the rear blade increases. On the front, lift decreases. On the rear, lift increases. So the front of the heli moves down and the rear moves up. The heli tilts forward. When swash plate tilts backward, pitch on the front increases and pitch on the rear blade decreases. On the front, lift increases. On the rear, lift decreases. The front moves up, the rear moves down, the heli tilts backward. As we saw for the collective pitch previously, let's see the effect of the cyclic pitch on the rotor area. On the left, the heli is hovering, lift is equal to the weight, and lift remains constant on the whole rotor area. On the right, we are giving an order to tilt the heli forward. So the swash plate tilts forward, and we notice that the lift remains not constant on the rotor surface. One side has more lift than the other side, so the heli tilts. But if you are attentive, you are probably surprised by the distribution of the lift. We want to tilt the heli forward, so the distribution of the lift should be in this side. Okay, separate here and lift less here and higher here. But in fact, we can see that it is shifted to 90 degrees. This is due to a physics phenomenon named gyroscopic precession. We will see that later. Now, let's explain the tail rotor. First, let's see the Newton's third law, who says for every action force there is an equal and opposite reaction force. So let's see what's happened on helicopter. When the rotor rotates, it tends to make the fuselage turning in the opposite direction. This is the torque. To counteract the torque, a small rotor is placed vertically on the tail of the fuselage. It tends to prevent the helicopter to turn. Now, let's see its effect. So, the tail rotor, not only it counteracts the torque, but we use it to turn the helicopter to the left or to the right. On the drawings, the black arrow shows the direction of the rotor. The red one symbolizes the torque, and the yellow one the tail rotor force. On the figure in the middle, heli goes straight forward. Tail rotor simply counteracts the torque. On the left, we decrease the tail rotor force. Then the torque has more power than the tail rotor, and the heli turns to the left. On the right figure, we increase the tail rotor force. This force is bigger than the torque, then the heli turns to the right. Finally, the last component we see now is the flybar. Here is the flybar with green paddles. The flybar is linked to the main rotor, and flybar and main blades rotate together. Flybar can be located below or above the main blades. Flybar rotates in a plane parallel to the main blade plane. Flybar has streamlined and ballast paddles. So this configuration gives the following effects. Flybar acts like a gyroscope and tends to keep rotor more stable. For example, heli has better resistance into the wind. Another effect is that the flybar provides force amplification that reduces the cyclic load on the servos. In fact, servos will control the flybar, which is lighter than the main blades. Just notice, before to see the next slide, that we can see that the flybar has an angle of 90 degrees with the main blade. This is to manage the gyroscopic precession, and we will explain this soon. Flybar. How does it work? On the figure, here is the flybar, and here is the main blade. In this case, the flybar is mounted above the main blades. We notice that the flybar is linked to the main blades with linkage rods. When tilting the flybar, the main blade pitch changes. When the swash plate tilts, the paddle of the flybar tilts, then the flybar tilts and modify the main blade pitch, which makes the main rotor tilt in its turn. So, we have seen the mechanism of helicopter. Now we will see some physics specific to helicopters. On aircraft, wings are fixed. On helicopter, blades are rotating. This creates some physics problems that we have to manage when we design helicopter. So, we will see what gyroscopic precession is. So, we will analyze a cyclic command to understand how gyroscopic precession is managed. And finally, we will see dissymmetry of lift and how to counteract it. Let's start with the gyroscopic precession. This occurs on rotating objects. This is the case for the main rotor. The phenomenon can be described like this. When we apply a force on a rotating object, the result force occurs 90 degrees later in the direction of rotation of the object. Here is a figure to illustrate this. The cycle is the rotor. The blue arrows show the direction of rotation. Let's say that I want to tilt the rotor to the right. Naturally, I apply a force downward to the right and a force upward to the left. Nevertheless, the rotor will not tilt on the right because forces will apply 90 degrees later in the direction of rotation. This force will apply 90 degrees later, so here, and this force will apply 90 degrees later in the direction of rotation, so here. Then the rotor will tilt forward. Now we know this effect, we can understand how a command to the cyclic will do to tilt the helicopter in the good direction. For example, we will tilt the heli forward. So, the green circle is the main rotor, and the yellow one is the flybar. The main rotor turns clockwise. Okay, the main rotor turns clockwise. First, the heli is hovering. The pitch is 4 degrees on the whole rotor. We apply the command to tilt forward, so the swash plate tilts forward and the flybar receives the order, and its pitch changes with +6 degrees here and -6 degrees here. Due to the gyroscopic precession, the flybar tilts 90 degrees later. Flybar turns clockwise, so the force here will apply 90 degrees later, so here. Then the flybar will tilt forward. When the flybar tilts, main blade pitch changes. First, the main blade was at 4 degrees and it changed to +9 degrees and -1 degrees. +9 degrees here, -1 degrees here. The gyroscopic precession will apply also to the main rotor, so this force here will apply here on the back, so the back of the rotor will move up, the rear of the helicopter will move up, and finally the helicopter will tilt forward. So, to summarize, we just need to tilt the swash plate in the direction we want to go, and the washout manages the 90 degrees shifting. the pilot don't have to think about this. Just one note: on flybarless helicopters, the shifting is made by electronic. Finally, I will explain a second issue, the dissymmetry of lift. There are a lot of other issues, but I will not explain here. So, the dissymmetry of lift occurs when helicopter does directional flight, when he is moving forward, for example. When the helicopter moves forward, it has a speed shown by a green arrow on the figure. The rotor turns clockwise, and it has a rotating speed shown with blue arrow. So blades have also rotating speed symbolized with blue arrow. On the left, the blade is moving in the same direction of the helicopter. This is the advancing blade. On the left, the blade goes in the opposite direction of the heli. This is the retreating blade. The airspeed is not the same for the advancing and the retreating blade. On the advancing blade, the airspeed is equal to the rotor speed plus the helicopter speed. On the retreating blade, the airspeed is equal to the rotor speed minus the helicopter speed. So, it generates a dissymmetry of lift between the two sides of the helicopter. I skip the next more complex figures. So to summarize, the airspeed is higher on the advancing blade, the lift is higher too, so the advancing blade tends to move up and the retreating blade tends to move down. To solve this issue, we had dampers named flap dampers around the feathering shaft in order to add degree of freedom for the blades. So, blades can flap without tilting the heli. Now it's the end of this presentation. Here are the sources I used to prepare this presentation. So first, I use Okapi. This is a scientific magazine for young people. I used also the article Débuter en hélico, meaning Start with Heli, by Stéphane Postigo. I used his pictures. And finally, I use the website Helicopter Aviation, which explains aerodynamics of real helicopters. Thank you for watching. I hope you didn't suffer too much with my bad English and you understood me. You can find this PowerPoint and other information on my website. Thank you again. Bye.